Okay, I think we are live. Hello and welcome everyone to the new episode of the AI co-learning program. I'm your host Bruce, and it's great to have you all with us again. Today we're diving into one of the most fundamental and rapidly evolving topics in AI: reward modeling. So, as reinforcement learning and alignment research continue to mature, understanding how reward pathways are defined and redefined has become central to building AI systems. So today we are truly honored to have with us Dr. Schrader, PhD in machine learning at ETH Zurich. His research focuses on reward models in machine learning pipelines, exploring the brightness of current models, current reward structures, and proposing new frameworks for rewards. So today he's going to share his insights on rewiring the reward pathways, how to rethink the foundations of reward models in AI systems. So, hi, Doctor. Thank you for joining the co-learning series. Now the floor is all yours.
Thank you. Thank you, Bruce. Thank you so much. So, as Bruce already mentioned, I'm Kumar Sridhar. I did my PhD at ETH Zurich in Switzerland. And today I'm going to talk about rewiring the reward pathways. And what this means essentially is, as we all know, reward pathways are kind of network inside our brain. So they are some form of dopamine system, which gives us some natural rewards, like I feel very pleasureful if I'm doing something which I really enjoy. So some kinds of social interaction is nice if I am eating my favorite food. So I get a dopamine hit. And then my brain is somehow telling me you should repeat those behaviors again and again because this is something that my brain likes, and I would want to reward my brain with these signals again and again. When we talk about LLMs or any kind of neural networks in general, so they also get this reward signals. We can design these reward signals ourselves, but then the goal here is we can guide or align the model to behave in a certain way. And whenever they behave in that specific way, we give them a positive signal. So if we want our models to be safe, so this is one of the AI safety is one of the concerns. And whenever we see that the model is behaving in a safe way, the way that we wanted the model, so we give it a positive signal. Similarly, if the model is not behaving in the way that we want, so we give the model a negative signal, which is same as, for example, if there is something that we don't like, so probably next time we are not going to try that food or some social company if we are not enjoying. So somehow we are giving this negative signal to the brain that this I regret this decision. That's what we often think about. So these kinds of reward pathways can also be designed in our language models. And then in this talk, I'm mostly going to cover some of the tricks, some of the ways to design these behaviors. Why do we need these behaviors? Some usefulness of it, and some very little practical insights on how we can start with this. And later on, there are, like, as you all know, a lot of research going on in this direction. We can always read those papers and improve over them. So when I start this whole thing about language models, it's important to understand the pipeline or how the language models are trained. So the training pipeline starts obviously from with the data set. So generally, the data set is a mix of different modality. You can also choose like text-only models or text and image models and so on. But then generally, the training data set we can think about as some form of modality that we all collect. This need not to be limited with text, audio, or images. You can, like, if you want to train a drug discovery kind of models, you can also feed a gene or DNAs or RNA sequences there if your goal is to predict the next sequence, let's say. But then the data set is basically, let's say, the building blocks of the model that we are envisioning that this model will do. And before we feed this data to the model, there is this whole pre-processing pipeline where we would like to clean the data, filter the data in terms of um, in like textual data set, we would be interested in removing all kinds of synthetic data set. We would be playing with different data mix. So that also means sometimes we would be interested in making the model learn some mathematical reasoning capabilities or some coding capabilities. So we would also come in and mix some of the data. There is fine web pipeline, which has been designed by Hugging Face. And then in this pipeline, you can see for text-based data cleaning, you can remove all kinds of links that you want. You can filter based on the languages. Personal information can also be removed and so on. So the goal here is to clean your data so that the models can learn a lot from the cleaner version rather than learning a lot from some noisy data. And once we have this pre-processed or clean data, we feed it in some form of a network. Generally, we know everything is based on transformers now. Without going into the architectural details, let's assume that we have some form of network which is capable enough to compress this entire knowledge that we are feeding into the model, and then we do the training of this model. What we eventually get is a base model, and this whole process is called the pre-training stage. And then for if we are considering our textual model, like some form of text-based model, the loss is a next token prediction loss. So essentially the model is trying to predict the next word, and we are essentially saying this word is correct or not, calculating some form of distance, how far you're from the actual word that we want the model to predict. And then this, we encode this in our loss, and we train the model. And this, when we test this kind of model, so the the question that I'm feeding here is a simple reasoning question. You can also see this is slightly trickier than what we expect. So for example, if you have 10 apples and if I have 10 apples and I give you 2 apples, how many apples did I give you? So that's the question, not how many apples are left with me. So a bit tricky. That's not the goal, but I'm just saying it's a very simple question. It's a retrieval question and not a numerical mathematical reasoning question. Right? So if you see the output, this is, I have also provided the link. You can also check this out. The if you go here and check this, the model will output something very gibberish. I also have this open, but I can show you really quickly here. So this is exactly the same model here. And if we want to, let's say, write something, so I would give this model exactly same question here, and then, oh, why is it saying me to? Okay, I am not logged in, so it's not allowing me. Sorry, it's a different laptop now, but basically you can go and try this out. So since the loss was next token prediction loss, the model is not capable of reasoning enough. So it has seen a lot of data like this on, let's say, some forums on Wikipedia, articles, some other form of documents. And then sometimes with a question, it is seeing the next question. And that's why it has started generating some gibberish. But you see, grammatically, it might be good, but like it is generating just the same question. So to solve this kind of problem where we want the model to follow a specific structure, given one kind of problem, we want the model to answer it, and so on. So we do something which is known as post-training. So what this does essentially is collect a lot of fine-tuning and instruction tuning data set. And this here, I'm showing an example, like with like keeping the same theme in mind, doing the math word problem instruction here. So we are giving the model that you need to solve this problem. So we are giving the model an instruction. The question is exactly very similar to that, like some cost we have to find out. And then the answer here is just step by step how the model would reason and eventually reach to the final answer. So now we are doing a post training on these kinds of data set, which consist of like instruction, question, and answer pair. And then now the model would be trained on this. So we take the base model that we have already trained, so the pre-trained model, and we do some form of supervised fine tuning and some form of instruction tuning over it. And the fine-tuned model that we get, if you give it the same problem, it would answer you in the right manner, the thing that we are expecting here. And the reason for this is now the model is trained on these kinds of downstream tasks, as they're called. And these downstream tasks are basically some form of instruction plus question answer pairs that we are training the model to behave in a certain way and answer the question in a specific style. So instead of math word problem, I can also give an instruction about summarization. And now, even if I give the model same problem, it would just summarize it because the ground truth data is more like a summary instead of reasoning and so on. Now, the question is, what if I want the model to behave in a specific way? So if you see for the same problem on the left, now we have two different solutions. Both of them are correct. Both of them are saying the same thing. But let's say there is a preference here, and I would prefer the second solution more because it's more cleaner and without those scores and so on. So it's my personal preference. You might also like question the solution number one. Totally depends. But I'm saying I am training the model for myself, and I prefer the second answer more. So I want to teach the model that you should pick this answer more, like the second one. And you should start giving some form of negative signals to the model that even though both of them are correct, you just up this one. So make the second answer go, the probability of getting the second answer go up a little, and then the first answer, make it go down. So directly doing supervised fine tuning won't work because it can or cannot, but the question is, so the loss that we are doing is cross entropy loss. So we are forcing the model to learn every word step by step. I'm not saying this would not work, but like this is somehow forcing the model to repeat exactly word by word what it has been said. A lot of times I don't want the model to be memorizing all the things that I'm showing it, but rather also generalizing a bit. So it should capture all the gist of the whole thing. I should capture my writing style, the way I want to communicate something, and also the correctness of the solution. But I also don't want to force the model to learn everything word by word totally. And as you can see, this goes in the direction of some form of alignment where we are interested in knowing how we can align the model to behave in a certain way. And this alignment can also be done over the fine-tuned model because now the model knows how to solve a problem. It's just we want the model to like to start behaving in a certain way. And later we also want the model to reason and improve their accuracy and so on. But like to start with, we want the model to align its behavior in the way that we like. And one of the popular methods for alignment, which started during ChatGPT era, that we call, is RLHF, which stands for Reinforcement Learning with Human Feedback. So I can go into the details of RLHF because it also forms the base for the reward models that we are going to talk about. So this works in three simple steps. So the first step, so this is taken from Instruct GPT paper. So you can also go and read this paper. This will give you a lot more information. But like the first step is the fine tuning step, which is very similar to what we did during post training. So the way it works is we collect a lot of demonstration data, which basically means I generate or I collect a lot of queries. For all the queries, I can write good answers to those queries the way we want the model to answer. And in human, um, a- as there is a human word in RLHF, we want the labeler or a human to write these answers for us. These are called ground truth because that's what we want the model to answer or behave in that way. And once you collect those data, you just make this question answer pairs, and then you just fine tune the model. So this is the same supervised learning objective. We are training this with cross entropy loss, and the model is kind of trained to answer the question based on the given problem. And then the next step is we take this fine-tuned model that we just trained in step one, and now we feed the model with some queries and we generate a lot of samples from the model. And then this generation can be done in a lot of different ways. You can have like a higher temperature where you want the models to generate some diverse samples, and you collect all these samples for a given problem. Now you go to the human again, and we say like, look, the model learned this in this specific way, and these are the solutions that we can generate from the model. Which solutions do you prefer? And now the labeler or the human can choose that I prefer sample one over sample two, and so on. Now we use this data to now train a reward model, which, like, the goal of this reward model is to just mimic the behavior of the humans, where it would take the question, take all the generated samples, and then would give us a score. Now this score would somehow like can be used to rank our solutions, and we want this reward model to be really strong in a way that it can imitate those humans. So then, given a problem and a bunch of different solutions, it can also tell us this is something that I like, this is something I don't like. Not necessarily the answer, like answer is one of the criterias, but like sometimes we are also interested in knowing the style that we are using, or the way we are writing things, longer, shorter, and so on. So it's just preference. So now our reward model is trained in this way. We'll go into details of how we can train this reward model later on. But then once we train the reward model, now we take our supervised fine-tuned model from the start. We feed a prompt, a new prompt, which is sampled from the data set. We feed this to the policy. Policy is the supervised fine-tuned model from the first step. So we feed this policy and we let the model generate something. Now, once the model generates something, we feed this to the reward model that we trained in step two just now. And we, based on the reward that we got, now we update our policy or the supervised fine-tuned model to behave in a certain way based on the rewards. Now the rewards can say that the model has done a very good job, so the model would keep on repeating this behavior. Or the reward can also say, this is something I don't like, and now the model would just go back and start changing itself, so that next time it generates a different solution, the reward model can, we can see if the reward is improving or not. And this way we can keep on iterating this, and we update the policy. This whole algorithm which we are using to do this is called PPO, and PPO means like proximal policy optimization. So this is the figure from the PPO paper back in the days, and I would like quickly go through this figure because this would give us a lot of insights on how reward model works and why this is something we are interested in our like LLM training and so on. So Q here on the left is our query. So the question this goes into the policy model, which is the model from step one. Like you remember the fine-tuned model, which has been trained on question and some solutions. And then now the model outputs O, which is the output. Now there are a bunch of models here. You can see like the reference reward and value. So we get the output, and then we basically calculate something called R, like some form of ratio, which is how much the new policies is different from the old policies. The ratio is just the ratio of like probability of old policy divided by new policy. And A here is the advantage. So we take the ratio of like our new, like the ratio of how, like the probability of new policy output divided by old one. And we multiply this with the advantage function to get us a value which we want to use to update our policy. This advantage, as the name suggests, is saying how good this current policy is compared to like an average or like expected policy that we already have. So this is essentially like in real life saying if I do something, how good I am then compared to like an expected version or like an average version which is expected from me. So think about if I'm running like 100 meters and if I complete something in 8 seconds, it is unrealistic. Let's say 12 seconds. And then there is an expectation that everyone should do within 13. So my advantage would be like I am 1 second better than the others. So this value model or the critic model here is something which is giving us like an average or expected value against which we see our like the new policy how better we are compared to this. So this value model is also trained together with this whole pipeline, but then given an output, we calculate the ratio, we calculate the advantage compared to the expected value, we multiply the two and update the policy. Now, the thing is, like, suddenly my policy model generates something which is amazing. So now my advantage would be great, and my policy would be updated suddenly by larger value. Essentially, we don't want this because then it has all these problems where sometimes you would just keep on going up, down, because sometimes your policies are really nice and sometimes it's not. So in practice, we also put a clipping function at the end, which basically keeps us within a value. And like you define a clipping value like epsilon, which allows you to not make the model go like crazy, but keep you within that range. And the um and then so this reward model, so this reward model in the middle, this is the model which we already have calculated before, like the model that we have trained before. So this take the outputs and give us a reward. And how good this reward is like already taken into account when we are updating our policy. This reference model is the model, the pre-trained model that we took, and then we fine-tuned it to get the policy model. So we, like, let's assume you are doing a pre-training over like trillions of tokens, right? Now, when you are doing the post-training, generally the number of tokens is lesser than the pre-training tokens. Now, the post-training tokens is moving your model in a specific way because you want the model to answer your questions in a specific way and so on. But you don't want the model to like forget what is it has learned over all these pre-training that has been done. So this reference model we use to keep the current policy in check by calculating something known as scale divergence, which basically calculates how different this current model is from the original reference model. And then just think about this as a regularizer or something to keep you in check so that you don't go a lot away from the old models. So yeah, so these all four models would make this PPO pipeline. And then this at the bottom is just a very simple way of showing this, where like you take an expectation, so you average things out for every question which has been sampled. So Q is the question sampled, O is the output which you sample from your policy. And then you calculate this ratio of your current policy over the old policy and multiply this with an advantage 80. And then since you don't want this to move like crazy, you also put like an 1 minus epsilon, 1 plus epsilon as your clipping value. And then you to take the minimum of these two so that you make your policy updates based on this. And then you also put a KL down. So this is all nice. I have put some links here. Like if you want to understand more about PPO, you can read this Sebastian Rashka blog. He has a very good way of saying or explaining PPO by giving an example of hotel restaurants and if you are a chef and how you calculate your advantages and how you update your policies. If you want to like do the practical implementation, this NNML has the implementation of PPO in PyTorch, so you can do this. And then you can also try and play around with all kinds of PPO and a lot of variants in like TRLO world. These are the libraries for doing a lot of reinforcement learning nowadays. So you can also try to play around with this in these libraries. But like in general, uh, we got this gist that like keeping all kinds of models in memory, at least a couple of them, so two of them are trainable model, is very expensive. So a good idea would be to like slowly move towards a system where you would have fewer and fewer models and you would be interested in making the whole system fewer memory better in terms of its memory and lower in terms of its compute cost, so that you can also iterate over this a lot more. So easiest way would be to remove this value model now. So it is a trainable model, and it's also its job is just to approximate the like the average value which over which we can calculate the advantage. So another version of PPO, like I would rather say an extension of PPO, came out, which is known as GRPO. And the only difference between PPO and GRPO is that there's no value model in GRPO. So if you don't have a value model, how would you calculate the advantage? Like how would you calculate the something which is an expected value over which you can calculate the advantage? So the change that GRPO made was you take a question and you generate multiple outputs. For all outputs, you can give different rewards. And here, let's say I generate multiple outputs and then I give R1 to RG, like all form of rewards. And now I have to calculate the advantage. So I would calculate the advantage over the average of all the samples that I have. And in a way, I'm saying that these are all the generations that I have and all the rewards, and how good each of my reward is over the average. And this would give me enough advantage to know that I should keep on generating this reward more and more, and I should stop generating something which is below my average. And yeah, and then you have a obviously a KL with your policy, and this way you can remove the value model or the critic model, and this makes GRPO more efficient than PPO, at least in terms of compute wise. And lately, a lot of experiments have been done, and GRPO performs at least as good as PPO, if not more. But since it is computationally cheaper, you can run more iterations with GPO and with GRPO, and that's very good. So, in short, my policy optimization pipeline with all these objectives involves a question, some form of generations using a policy model or a generator model, and then a reward model that we can train in different ways, which would be used to assess all my outputs in different ways, right? And then give us a final score of saying, oh, these whole generations I really like, this generation I didn't like, and you can then do something over it, let's say. And let's say now I have like something like a math word problem that we have been seeing again and again. So for those math word problem, I can use my policy to generate a lot of generations, and then you don't even need a reward model if you ask me, because everything you can verify if the output is correct or not, because these are simple computation, right? So using an expert or like a deterministic method like a calculator would like always give you this output that something is correct or not. And this correct or not is basically the job of the reward model. But now you can also put a deterministic system there. And then if you need to update your policy, so you can do this, because now you are generating a lot of outputs. All the outputs you can get 0 1 reward, because every output you can verify. And then you give the signal to the policy model that these are the outputs which are correct, these are the outputs which are not correct. This is not necessarily doing alignment, because this is not saying I would prefer O1 over O2 in terms of their style or the way it is constructed, but it is giving us a signal that I would prefer O1 over, let's say, O7, because O1 is correct and O7 is incorrect. So this is something known as RL with verifiable rewards. The reason I'm showing this is now you have removed one more model from the whole pipeline. So you can also remove the reward model. So previously you removed the value model or the critic, and now you can also remove the reward model, and you can just have a policy, and then you can always have a KL term, because you don't want your model to go a lot away from the whole true model. But now you can also remove one more models. And this RLVR style training was very popular with like O1 style models in GPT series. It was also popular with DeepSeek R1, which brought this whole revolution with RLBR style training. And this on the left side, you can see RLHF, and on the right side, you can see RLBR, with the major difference being you need to have a reward model for RLHF, but for RLBR, you can just skip the reward model completely, and you can just create a system of verifiable reward where you can do some simple regular expression matching, some calculator, some deterministic way of knowing if something is correct or not. This also means that you don't have to create a lot of data set, like some form of preference data set to train your reward model, because your verifiable rewards need not to be trained, right? Like the system need not to be trained. It can figure out whether the answer is correct or not and give you some scores. And rest everything is kind of similar. And this kind of a mixture of RLHF with or without RLVR. So these kinds of verifiable rewards was used in DeepSeek R1. Especially RLVR was used to train DeepSeek R1 0, where they took a previous model like V3, and then they would start generating a lot of output samples, and they would check if the output is correct or not, and they keep on repeating this problem. The only thing was R10 was not very consistent, because at the end, you are only outputting a correct sample towards the end, and you are not checking if the intermediate steps are correct or not. So it had to be trained a bit so that it can generate something correct, like when it is thinking or when it is generating the intermediate step. And they say there is like some form of cold start data which they use to train this model to make it be more accurate. And once it was done, then they did a lot of RLBR, and then they combined also with some RLHF, because you also want the model to behave in a certain way, and that's how you get the DeepSeek R1. So that was a combination of RLBR plus RLHF with a bit of cold start data which was collected to start the whole process. And before I wrap this section off, I just want to say, if we look deeply into the Q and O, like the question and the output again, so you see here the question consists of like a bunch of different steps, um, not different steps, but I would say a bunch of different context which is provided in order to generate an output. And output, you need to solve like a bunch of different steps before you can reach to the final answer. So in short, the question is like providing us some information using which we solve the given problem with different steps. And in this case, we require 2 steps to solve the given problem. And then you can feed your final answer or even your equation, because if the model, let's say, is really small and is incapable of solving it, that's okay with us. You can also provide 0.2 into 5 into 50 as the final answer, and we can run it through a calculator and say the answer is 10, and the answer is good for us. So we don't care about anything else. We just care about the final answer is correct. But like, as you might have noticed, this is a bit of a problem, because even if your steps are incorrect, which means you are generating gibberish here in between, but then you eventually reach to the final correct answer, or the final equation is correct, you can still feed this to a calculator, and the calculator would say this is correct. So this is a way of only judging the outcomes and not the intermediate steps. And these kinds of models are mostly known as outcome based reward models, whose job is to just look at the final answer and or the final generation, and then based on my final generation, I can say if something is correct or not. And usually it is very beneficial for, let's say, those cases where without getting all the generations, I cannot make a decision. So let's say if I have to do some form of preference base settings where I have to check whether A is better than B or B is better than A, I need to look the entire outcome to make a decision. Or like if you are asking me to do a summary of something. So I cannot look at just step one and say, oh, the summary looks good, or if it is going in the correct direction. But I have to look over all the steps and find an answer, and then I can say if something is correct or not. And then something like RLVR setup that we talked about, if the reward is verifiable reward, so you have to look at everything, and then you can make a decision. Like if um, intermediate steps is not verifiable, like for example code, if you are writing some code blocks, unless you can run those code blocks, it's like kind of impossible to say in the middle if something is correct or not. But like if you can design a system where every step is verifiable, so mathword problem goes in this direction mostly, where you say if step one is good, step two is not good, and then the answer is correct or not in a similar way. So these are known as the process reward models, where you can also design your reward models, which can look into the intermediate steps and give you um, a rating over those, like if something is correct or not. So the next section that I want to talk about quickly is understanding all the different kinds of reward models, whether it's a process based or outcome based, designing a reward model for to be part of like a training pipeline like RLHF. How do you design these reward models, or which kind of considerations you should have before you jump on and start modeling this? So the first use case would be you give an input X and an output Y, and then you feed this to a model, which would consist of, so this reward model would be, it can be any kind of model. Let's say you're doing a transformer based model. So then your job would be to fix this and train a head or put a classification head at the top, whose job would be to estimate how good this output is given the input. So you would like to estimate the probability of your output Y given something. So one example for this kind of model would be I give an input and I give an output to a model, and this reward model should give me the score, like out of 5, how would you rate my model? So these models are known as the discriminative reward models, where where we are doing a direct assessment of how good my output is given an input. And you take a base model, the one model that we pre-trained, then you put a head over it, so some form of like MLP based classification head at the top, and then you output a scalar value saying how good the score is. Another kind of reward model in similar direction is, now you have two inputs, so you have uh, not two inputs, sorry, two outputs given an input. So given an X, now you generate Y1 and Y2, so two outputs. And now you have to model this probabilities that one output is better than the other. So this is kind of useful when you generate two outputs, and you have to choose one. So some form of preference alignment goes here, or in general, from two systems, you are getting two outputs and you just have to rate them or rank them. So these are some form of pairwise ranking models. And this is just another version of discriminative reward models, where we take comparison as inputs. And then our job is to select the best candidate out of the two. You can also do the same thing here, where you feed X and Y1 first, and you feed X and Y2 again, and then you take their probabilities and then you just compare them. So that's also possible. And some libraries like TRL, so very simple libraries would work here, where you can feed the inputs, and you like, before even feeding the input, you would want to train a model which would take the input, take the output, and give you a score. And now, with all these libraries and all these wrappers, this can be implemented literally in like 4 lines, which essentially looks something like this. So you load some dependencies, you define your trainer function, which would load the model and load the data set, so things that you really care about. You obviously need to create all those train test and validation split just to check things and um, see if the model is overfitting or not, and all the other criteria. But literally, you can just call this trainer function with the train command, and that would train the model. Some of the consideration that you should care for such systems is when you are choosing the model, you can load any model you want from Hugging Face, but it depends on the budget, whether your computation, like a model fits within your computation budget or not. It also depends like how big of context window you want, which kind of tasks you care about, whether it's a math word problem, some form of reasoning, or whether it's some form of preference where you are choosing which, for example, story is better for a given prompt and so on. And then for the tokenization part, you use the same tokenizer that the base model has. So you don't have to write your own tokenization and so on. And then you define your data set, which can be in like a simple prompt and response format, or it can also be a conversational format where you define the role of the user and assistant. And with both of them, you have to define which one you choose and which one you reject. Because this is what the model will learn. So it will try to assign higher probabilities to the chosen one, and it will try to reject the other sample, which is incorrect. And you can design the data set easily if even if you have your own file which contain some data set and so on, you can just import them. Like Hugging Face also have a data sets function which expect things to be in a specific order, but then this is really fast. So you can just like import your own files and just make it a data set format. And then you define your loss function where your goal would be to maximize the probability of the chosen one and to reduce the probability of the rejected one. So for a given response, your reward model with parameter thetas will with parameter theta would try to assign or maximize the probabilities for your chosen one and try to um, reduce the ones for the rejected response, which in like a through a sigmoid function, this looks something like this. So you define the sigmoid function, and then you want to maximize this difference between your chosen and rejected one, so that you can clearly choose one samples and you can clearly reject if it is not falling within your preference range, let's say. And this is like very simply done through Bradley Terry function. Like it's really standard, which is being used everywhere nowadays. So you can design this and this works. But then these are all the like the discriminative models. But you can also have generative models. Like for example, you feed your input and two pairs of response. Maybe one is correct or something that you prefer, one is something that you don't. And you can also train your reward model to be more like a generative model, which it can say, I prefer y1 over y2. It can also state its reason. And this goes inside the generative reward model category, where we can leverage the generative capabilities of LLM to give us like preference scores or saying I prefer this over that. You can also take out the logits if you want, like if you want the probabilities, how much I'm assigning to yes versus no. So you can also take out the logits and also play around with that. And these kinds of generative systems would require like a couple of things. So it would require a system message at the top, which is basically giving some instruction of what you are and what your job is. And this would consist of a lot of instruction on how you can judge the outputs that I'm providing you, what are the criteria for my ranking, because like one answer is worse than the other answer only if you can verify this. Let's say for mathematical reasoning, you know, answer one is incorrect, answer two is correct, so you can directly say two is better than one. But let's say if I'm writing a summary, or if I'm writing let's say given a prompt, I'm writing a story based on that prompt, so you cannot say, you cannot verify that my story is better than yours unless you have some criteria, some instruction of how you want me to rank. So this is very important. You define some rubric or some instructions for the scoring. You provide two outputs to the model, and then the model would give you a score. You can also ask the model to give you a feedback or to choose A over B. So one of the libraries that does this, it's called Prometheus. You can find this on GitHub easily. Um, Again, it works really, really simple. So let's say you have already trained your models as a judge. So let's say you have a model which is very good in terms of judging whether this output is good or not. So you load your model and then you provide your instruction set. So you provide how you want to test the model. You provide your rubric data, which is like criteria for judgment, and saying, I want you to give me a score between 1 to 5, where 1 means this is really bad. These are the conditions. 5 means really good, and this is what I want you to check against. And you give an instruction, you give some rubric. Now you have a reference answer which you say, this is what I would classify something as. Let's say for story generation, this is a quality story, so this is 5. And then you take everything, feed this to a model, where the model would take the instruction, take the rubric, take the response that we want to give a score on, and take my reference answer, which kind of saying this is how 5 would look like, and this is your output. And this would give out a score. Let's say if you have defined your score between 1 to 5, so it will give you a score. And then it would also give you a feedback of why the model thinks this score should be assigned to the given response. And this is based on how the model was trained. But like, think when you are training the model, you can create like a fine-tuning style data set where you will have some bad stories, some good stories, and then you can output a score, and then you can output a feedback. So you train the model to output a score and a feedback, and then this can work when you do this in practice. So yeah, this works for both. It can work for pairwise ranking, so whether A is better than B or not. And this also works for the assessment, where it would give you a feedback and would give you a score. Now, when I talked about the reward models, different kinds of reward models, how we model this, and all kinds of training strategies using reward models, there is a small issue. As our brain learns to take shortcuts, which sometimes ask us to repeat some action again and again, which is giving us a positive reward, and um, our brain is somehow exploiting this pathway where we are over compulsively seeking those positive behaviors, and sometimes this leads to some form of addiction. This is a similar problem that LLMs or any kind of neural networks also face. So, for example, if I'm designing a coding system, and the criteria to say whether this is good or not is to pass all my unit test. Now, this model would say that if I can change the unit test in a specific way, that I can always pass this test. So the model is somehow learning to trick itself. Or if I'm generating summarization and scoring it based on some rouge or some blue score, so now the model can also learn to explore some flaws, that if I do these things, I'm getting higher scores. So it is just repeating those behavior where it is giving me some gibberish output, but really, really high scores. So let's say a story about basketball, and if I write basketball word a lot, I'm getting very positive response. So everything else is gibberish, but a lot of basketball, and that give me a good score. So the model also learns to bypass the systems and hack our reward pathways. And a lot of papers have worked in this direction. Like, for example, there were a lot of responses that someone gathered from Claude and GPT style models, where if the human says something like, I really dislike this argument, or I really like this argument, then the model would behave in a similar way, and it would try to answer that. If I say I dislike this, it also says, yeah, I do not find this argument very convincing. Or if when I say I like this, then it says this is a strong argument. It's also known as sycophancy, where the models become more and more sycophant, where they try to like please the user that is using it. And internal monologue for these models were also recorded, where the internal monologue for these models was saying, this is something that I don't like, but then it is saying, oh, but I don't want to hurt someone's feelings, so let me give it a very high score. So this is also another form of tricking the system. And one very prominent example of this kind of behavior, which we can also see, is like the model is generating something, so the policy, and then the judge is also same model. The model somehow learns to give a very high reward to something that it has generated by itself, and then it goes into this iterative loop where the model can generate like not that great samples, but then the judge would figure out that it is generated by the model and I should give it a positive feedback, and goes into this loop of not learning basically, and then just exploring the reward pathways. So reward hacking or reward tempering are the two big problems in uh, designing the RL systems or some form of reward functions. And in hacking, the model exploit any kind of flaws in the reward function. And in tampering, the model modifies the mechanism of this administration with the same goal in both the cases where it want to hack the system, get the best scores, and um, sorry, and just wants to maximize the reward. So I would like to go towards the end of this talk by saying, like, can you figure out all the different kinds of ways in which you can counter these hacking? And multiple reward models instead of a single reward model is one of the ways which has been shown to work. So this is one of the paper where the goal was to find the most suitable model for a given input. And if you judge these outputs by a single model, so a lot of times your reward model would have some form of biasness. Let's say your reward model comes from a GPT family, so it would start giving higher scores to GPT generated outputs and would pick this model more often. But then if you design a set of judges as reward models, where it can judge on different criterias and it can remove any form of hacking or biases the model can carry. And if you average out those rewards, you can get like a much better final selection. And this is one of the ways to counter reward hacking. Other ways include some form of capping, which we also see in PPO and GRPO. Training with counter examples, where we are also showing the model that this is not exactly what you will get all the time. So it does not exploit that specific thing. Or you design your reward models nicely and you look into the outputs, the solve is a good way, and you design, do very careful engineering to counter this. All in all, there are some flaws, but reward models are very useful. For example, they are very useful in annotation, where they can serve as a proxy for human evaluation. This can speed up the process. You can make things faster, of course, but also way more cheaper because you don't need human in the loop. They can work 24 hours. And you can also design your reward models, which can be expert for different things. And you can also remove any form of biases which humans sometimes carry. So if you design properly, these reward models, of course, are really good for various use cases, including annotation, and also very good for training larger models. So we know RLHF is really good, where you also need like human feedback to get everything. And there has a lot of research done with RLAIF, where now you're instead of humans, you can use some LLMs to give these rewards or give these scores, and then you train using this like AI feedback instead of human feedback. So you are again removing the human from the loop, which is very useful and making the process again really fast. And finally, I would like to say that if you end up making your reward models with any of the approaches, with any kind, you can go out and test your reward models on something like Reward Bench, which consists of a lot of chosen and rejected samples for a given prompt. And then you can go out and test your reward model where it can give you some scores for like either one of the chosen and rejected prompts, rejected outputs, and then you can compare the win probabilities of picking the chosen one and select and rejecting the rejected samples. And this way, you can calculate your accuracy. And there is a new version for Reward Bench called Reward Bench 2, where they have the authors have changed the whole pipeline with more difficult problems now. And then this also have like in other than complexity, other problems where for a given problem there is one chosen answer and all the ones are other ones are wrong, or multiple correct ones and multiple wrong options. So the goal is to pick the right ones and reject the correct ones. And you can go and check this out. Yeah. So I think we are on time. So I would like to thank you for joining. And it was a pleasure to talk about word models. You can also find me on X. My handle is Jupiter AI with Y, JUPYTER AI. And if you have any questions, if you're interested in this field, please ping me there. Um, we can connect there. Yeah, perfect. Thank you so much.
Yeah, thank you, Doctor, for the inspiring talk. I think we're now open for the floors for questions from the audience. Guys, please drop your questions in the live chat. So, the first question we have here is, in current machine learning pipelines, how do reward models influence the overall behavior and alignment of large models?
Mm-hmm. Um, there is a so this is a very good question. There are a lot of research done for different models. I would say there's one paper that came out, I think, yesterday or day before, where they are talking about all kinds of large language models and seeing which kind of behaviors are induced in these models and how these models behave in different ways. So current training pipeline is like pre-training where you feed all kinds of data into this model. Then you do fine tuning plus instruction tuning where you would want the model to behave in a certain way when you are asking the model a question. And then you are doing this alignment where these reward models comes in, like if you're doing RLHF or with like any of the algorithms like PPO, DPO, or all the modern new ones, their reward models would come into the picture, and then you would do RLBR over it to make the model a reasoning model. So there also some form of reward model is also used. But mostly when you're doing RLHF, you are training the model to behave in a certain way. So if I am asking a question that the model should not answer, so I'm aligning the model to say that I cannot answer this question. So people call it red teaming, asking it to not always say that I agree with your answer, but sometimes also counter you. So this is also some form of alignment. So these all are done during this RLHF time, where like the reward models are really useful. And I think all the language models which are out there, they all do this alignment, and that's where they use. I don't know if I answer your question, but this is the main stage where during the alignment, a lot of like doing RLHF and even now RLAIF a bit, they use like reward models a lot.
Yeah, I think that was very clear. So, let's see. The next question we have here is, uh, why do you think existing reward models tend to be brittle? Is it because of the data issues or model architectures or just misaligned feedback loops?
Right. This is a very good question. In my opinion, there are these rewards which you can verify. So, for example, mathematical reasoning, coding, and so on. These kinds of problems, you can easily collect a lot of data because you can generate a lot of samples. You can use a fixed system to verify if something is correct or not, and then you train your models. So, current reward models are really good with something which is verifiable, like, for example, reasoning models can easily figure out if you made a mistake. They can even solve like mathematical Olympiad questions and so on. But as soon as you go to something which is non-verifiable, like, for example, I write something and you write something, we don't know which one is better. It's just based on my preference. Or my intermediate steps cannot be verified because you don't know if this is correct or not. So there is not a good way that we have figured it out to model this behavior in the reward models, and that's why they are brittle for something which cannot be verified. Like, if I am trying to design a model which is like, if the reward model is to give a rating for something is toxic or not. So it's kind of very difficult for us to design the data set using which we can train the model, because you need human labelers to write everything. There is no way to verify whether this is like a chosen sample is non-toxic and rejected sample is toxic. So since we cannot design the data, we cannot train the models, and thus our models are kind of bad there. But they are really good, as you all know, for like reasoning tasks because you can verify that. So yeah, reward makes sense there.
Could eventually serve as a foundation for value alignment across different agents.
Oh, the I could not hear the last part. Sorry, please can you repeat?
Oh, sorry. Let me repeat again. Do you think unified reward models could eventually serve as a foundation for value alignment across different agents?
Um, I think so. The problem is how we create the unified reward models, in my opinion. Let's say I am creating an agent for, let's say, using my computer. So a computer use agent would explore a bit. So it would go to some links, click, and say, I do this. Then the behavior of my agent would be, maybe I'm not satisfied here. I can also click more. It might also be possible that I was on the right track and then I again explored a bit more. So, designing a reward system which is a mix of PRM and ORMs, where at individual steps I can check that I'm going in the right direction, and eventually I am also going in the right direction, would mean this kind of reward models would be unified models, which would have both characteristics of judging my intermediate steps and my final steps. If we figure out this problem, then I think they can play a big role in shaping how well the agents can work in different scenarios. Because currently, backtracking with these agents is a problem. If I am going in the wrong direction, but I cannot judge that I'm going in the wrong direction, and I am obviously not reaching to my final output, so the agent would just keep on exploring too much. That's very costly and sometimes would never reach to the answer. So saying that this is wrong, now you backtrack, this was correct, till the steps things were correct, you go back here and then start something. So that would prove to be really useful, but then that comes at the same cost, that can you verify that these rewards are correct, and can you create data sets for them? If you can, then these would be really good, I would say.
Okay, I think that brings us to the end of today's lecture. Uh, Huge thanks again to Dr. Friedher for sharing his expertise on reward models. We'll share the replay and slides through our community channels. So don't forget to follow us on socials, join the Discord and Telegram groups. Stay tuned for the upcoming episode. See you guys.
Thank you so much.
Thank you.
Bye bye.